In the previous section, we evaluated limits by looking at graphs or by creating a table of values. Now in this section, we are going to create some laws for calculating limits algebraically, and we're going to learn how to apply these laws so that we can precisely evaluate a limit. So the first rule that we're going to talk about, we want to assume that A and C are real numbers. So the first rule is that if I find the limit as x approaches some value of A using the function x, since x is just a line and there's no asymptotes or open holes or anything like that to worry about, the value of the limit at x equals A is going to be just A. The second rule is if we have a constant line, a horizontal line, and I find the limit as x approaches A on that constant horizontal line, because no matter what value of x you choose, it's going to be the same y value for that horizontal line. Our value for the limit at x equals A is going to be C. So here's some examples. If I take the limit as x approaches 2 of x, that's going to be 2. And here's an example for the constant function. If I take the limit as x approaches 2 of the constant function 5, that value will be 5. Now, for the next set of limit laws that we're going to go over, we need to set some ground rules. So we're going to let f of x and g of x be defined for all values of x that is not equal to A, which is the value that we're approaching. And this has got to be on an open interval. Containing A. So this is a fancy way of saying that all the values that are in the area of A for x, all those function values need to be defined except for that value that we're approaching. Okay, the other thing that we have to say is that the limit of f of x as x approaches A has to exist, and we're going to give it a name. We're going to call it L. And the limit of g of x has to exist as you're approaching A, and we're going to call that limit M. So the limit has to exist. Okay, so first rule is called the sum law for limits. So if I'm taking the limit as x approaches some value of A of a function that has been created by combining f of x and g of x with a sum, if I want to take the limit of this new function, if these previous conditions hold, if the limit exists for f of x and g of x at that x equals A, then we can say that the limit as x approaches A of that total function f of x plus g of x can be written separately. So I can write this as the limit as x approaches A of f of x and add that to the limit as x approaches A of g of x, which would be just the sum of their limits separately. I would take L and add M. So we'll call this rule number 3. Now the same holds for subtraction. So what I'm going to do is I'm just going to add a minus under here and say that this holds for subtraction too. So if the limit for f and g both exist, and I have the limit as x approaches a of some combined function, f of x minus g of x, I can split it up separately and say the limit is L minus m. Now we're going to talk about, we'll call this rule number 4. We're going to talk about the constant rule. If I take the limit as x approaches a of some constant times f of x, so let's say it's 3 times f of x or 7 times f of x. If that limit f of x exists and those previous conditions hold that we talked about, then I can say that the limit as x approaches a of c times f of x is just c times the limit as x approaches a of f of x. So I could just take that constant times the value of the limit. So I can take c times L, since L is the limit of f of x at x equals a. Okay, rule number 5. This is called the product law for limits, which is pretty much the same as rule number 3. This holds for multiplication as well. If I take the limit as x approaches a of f of x times g of x, if those limits exist for f of x and g of x separately, and all those values are defined in that area except for the value of a can be defined, but it doesn't have to be, then I can separate this and say, well, the limit of f of x times g of x can be written separately as the limit as x approaches a of f of x times the limit as x approaches a times g of x, which would be L times m. Same thing holds for division. If I have the limit as x approaches a of f of x divided by g of x, I can say that the limit as x approaches a of f of x over g of x of that combined function, I can write it separately as the limit as x approaches a of f of x divided by the limit as x approaches a of g of x, which would be L over m. But that's provided that m does not equal 0, because remember, we can't divide by 0. So there's that one extra rule that we have to consider, that won't work if we divide by 0. But any other case it would work. Okay, rule number 7. This is the power rule. If I find the limit as x approaches a of some function raised to a power, I can rewrite that as the limit as x approaches a of f of x, take that limit and raise that limit to the nth power. And this only works if n is positive or if n is negative, the value of L cannot be equal to 0, because remember, if you have a negative exponent, that means you're flipping it upside down and you're taking the reciprocal. So if your value of the limit is 0 and then you reciprocate, that you're going to run into a problem. So you got to make sure that your n is positive, or if your n is negative, that you're not flipping it and creating a 0 in the denominator. Okay, last rule that we're going to talk about for right now. There's a couple others that we're going to talk about later, but there's something else that we have to talk about first called continuity. But this is the last rule we're going to talk about in this section. It's the root law. If I take the limit as x goes to a, and I take some nth root of f of x, I can find the limit as x goes to a of f of x, and then take the nth root, which would give me the nth root of my limit. But remember, you have to make sure that you don't get any negatives under even roots. Right? Because that would walk us into the territory of imaginary numbers. So we want to make sure that if I take the square root or the fourth root of something and my limit is negative, that's going to cause a problem. So I want to make sure that my limit is positive if it's an even root, or it can be negative if n is odd. Okay, now that we have familiarized ourselves with the limit laws, we are going to practice applying these limit laws to evaluate limits. So the first one we're going to start off with is pretty simple. We're going to find the limit as x approaches negative 3 of the function 4x plus 2. So we're going to apply the limit laws one step at a time to make sure we understand how they work. And then we're going to keep in mind the requirements we need for each of the limit laws so that we know that they can be applied. So we're first going to start off and notice that this is a linear function, and linear functions don't have any breaks or holes or any unusual circumstances that we have to be concerned about. And if I look at 4x and 2 separately, I know that those limits would exist separately. So I can use the sum law and say, well, the limit as x approaches negative 3 of the function 4x plus 2 can be broken up into the limit as x approaches negative 3 of 4x plus the limit as x approaches negative 3 of 2. And that's using the sum law. Now, I can use the constant multiple law, where we have a constant in front of our function. That's the 4 in front of the x. I can pull that outside, and I can write that as 4 times the limit as x approaches negative 3 of x. And I'm just going to carry down the limit as x approaches negative 3 of 2. So all I did was use that constant rule. And now I can just use the basic limit laws, the first two that we covered up here. Let me scroll back up here. These were the basic laws right here, that if I have the linear function x, I can just plug in a to find my limit. And if I have a constant function, no matter what that value of a is, it's going to be the value of that constant. So, if we scroll back down here, I can write that 4 times the limit of x approaches negative 3 of x, I can write that as 4 times negative 3 plus the limit as x approaches negative 3 of 2, that's just my constant rule. I can just write that as 2, and I get negative 10. Now the next example, again, we're just using the limit laws. We're just going to have to use it multiple times. I'm going to find the limit as x approaches 2 of 2x squared minus 3x plus 1 over x to the third plus 4. So we've got a rational function here. Whenever we're dealing with rational functions, we do have that concern of having 0 in the denominator. So we have to keep track of that and make sure we're careful. So at the value of 2, as x approaches 2, I don't have any issues here. So I don't have a concern in the area of x equals 2. So I can apply my laws here. So I'm going to first apply that division rule, or the quotient rule, okay, because I know that I'm not going to get a 0 in the denominator. So I'm going to take the limit as x approaches 2, and I'm going to split it up where I have a limit on the top and a limit on the bottom. 2x squared minus 3x plus 1 divided by the limit as x approaches 2 of x to the third plus 4. And again, I can do this because I'm not concerned about getting 0 in the denominator in this case. So this is the quotient rule. Okay, the next step, I'm going to apply the sum and the constant multiple law. I'm going to break up the top here first. I can create the limit as x approaches 2 of 2x squared as 2 times the limit of x squared minus 3 times the limit of x plus the limit as x approaches 2 of 1. I'm just breaking it up using the limit laws. And then same thing on the bottom. I can rewrite this as the limit as x approaches 2 of x to the third plus the limit as x approaches 2 of the constant value 4. So that's using the sum and your constant rules. Okay, now we're going to apply the power rule because we have x squared and x to the third. So I am going to take 2 times the limit as x goes to 2 of x, and I'm going to square that. I'm not running into any special cases or any zeros in denominators or anything goofy like that, and I know the limit as x approaches 2 at x squared exists, and I can take the limit and then square it. So I'm going to do the same thing on the bottom. So I can take the limit as x approaches 2 of x and then cube it. And then I can add the limit as x approaches 2 of 4. So this was using the power rule. And now we have everything broken down into the basic limit laws, so we can simplify. I know that the limit as x approaches 2 of x is just 2. And if I square it, I get 4. And then I multiply it by 2, and I get 8. I know that the limit as x approaches 2 is 2, and then I multiply it by 3, that gives me a 6. And using the constant rule, the limit of just 1 as x approaches 2 is just 1. Same thing down here. This gives me an 8 plus a 4. And so when I combine all this together and simplify, I get 1/4. So from this step to this step, I just use the basic limit laws. The first two that we had up at the top. You want to break everything down to those two rules. So as we have seen previously, to evaluate the limit of a polynomial is fairly simple. Let's look back up here. This example here is a polynomial. And the reason why polynomials are a little bit easier to evaluate is because we don't have any special characteristics such as asymptotes or holes that we need to be concerned about. So we can use pretty much just direct substitution. When we start looking at rational functions, we have to be a little bit more careful. Like in this example, we had to make sure that we were not going to get 0 in the denominator in order for us to be able to use our limit laws. So here's an example of when we have to be careful of getting 0 in the denominator. So if you notice, I have as x approaches 1, that would create a problem and I would get 0 in the denominator. So I wouldn't be able to use my limit laws here. So what we have to do is use some algebra manipulation to see if we can reorganize this function so that we can evaluate it without worrying about having 0 in the denominator. And this is where it's really handy to have a good foundation of your algebra skills. We are going to factor x squared minus 1 over x minus 1 and see if we can simplify this in a way that makes it so that we do not have 0 in the denominator. So the top is the difference of squares. So I can factor this as x minus 1 and x plus 1. And in the denominator, I have x minus 1. Now, because I have the same factor of x minus 1 on the top and the bottom, I can get rid of it. And I'm left with x plus 1. If you think back to algebra class, and you remember graphing rational functions, these two graphs are exactly the same except for the fact that the rational function graph has a hole at x equals 1. This is called a removable discontinuity. So if we look down here, here's the graph of x plus 1 after we simplified it because we got rid of that denominator. And then here's the graph of the rational function before we got rid of that x minus 1. The x equals 1 doesn't exist on this graph. There's a hole there because it's undefined. So these two graphs are identical other than the fact that we have a removable discontinuity. So now what I can do is I can take the limit as x approaches 1 of just the function x plus 1, knowing that I rearranged it in a way so that their limits are equal, but I don't have to worry about getting 0 in the denominator. So now I can use the limit laws here. So I'm going to break this up, this sum, into the limit as x approaches 1 of x plus the limit as x approaches 1 of 1. Now I can use the limit laws because I'm not worried about dividing by 0. And so now I'm going to get 1 plus 1, which is 2. Now if we look at the graph as x approaches 1 on this function, which is what we're trying to take the limit of, we're trying to find the limit as x approaches 1 of x squared minus 1 over x minus 1. If we look at this, our calculations work because as I trace this graph coming from the left approaching 1, I'm getting closer and closer to 2. As I approach 1 from the right, I'm getting closer and closer to the y value of 2. Now because there's a hole there, the function value doesn't exist, which is why we ran into the problem of using the limit laws. However, that doesn't mean the limit doesn't exist just because we can't use the limit laws. It means that we had to use a little manipulation to figure out what the limit was. So you can clearly see from the graph that the limit from the right and from the left are both approaching 2 as x approaches 1. So that means the limit as x approaches 1, the two-sided limit exists, and we know that it's 2. So we verified it both ways, from the graph and using our algebra and our limit laws. Now there are some other algebra tricks that you can use to manipulate the expressions in order to use the limit laws if you're in a position where you can't at first. So here's a specific example of where I can't use direct substitution in the limit laws because if I plug in x as -1, I'm going to run into a problem of having 0 in the denominator. So one method we already showed you how to use was factoring. Another method you could use is conjugates, and this usually works well when you have square roots involved. So just a quick refresher, if you don't remember what a conjugate is an expression that is similar. It's the same expression, but the middle sign is different, and just the middle sign. So for example, x plus 7 would have a conjugate of x minus 7. So not both signs change, just the middle sign. Another example might be 1 minus the square root of x has a conjugate of 1 plus the square root of x. So these are conjugates. Now I'm going to take and manipulate this expression of the square root of x plus 2 minus 1 over x plus 1. I'm going to try to manipulate this expression so that I can rearrange the denominator so I'm not going to get a 0 when I plug in -1. So I'm going to multiply both the top and the bottom by the conjugate of the numerator. So the conjugate of the numerator would be the square root of x plus 2, and then I switch the sign of the minus. I'm going to make that a plus 1. And I have to do the same thing to the top and the bottom. Okay, when I multiply that out, because these two expressions on the top are exactly the same, but one's plus and one's minus, what happens is you take the square root of x plus 2 times the square root of x plus 2, which gives you x plus 2. The middle terms cancel out because they're exactly the same, but one's plus and one's minus. And then I have a -1 times a positive 1, which gives me a -1. So it's the same idea as if I were to distribute the x plus 2 times x minus 2. I have x times x, which is x squared. I have x times minus 2 gives me a minus 2x. 2x. And then the 2 times the -2 gives me a -4. And because there's the same exact expression, but with different signs in the middle, the middle terms disappear and add to 0, and I'm just left with the product of the first two and the last two together. So what I end up getting in the numerator when I multiply that out is x plus 2 minus 1. Then in the denominator, I get x plus 1 times the square root of x plus 2 plus 1 multiplied together. Now, if I simplify the top, I get an x plus 1 So now I have the same factor on the top and the bottom, so I can get rid of the x plus 1. And I've just simplified that expression so that it looks like this now. So I have 1 on top and then over the square root of x plus 2 and then plus 1 on the bottom. Now let's try to take the limit now that I've rearranged this expression. So I'm going to try to take the limit as x approaches -1 of my new expression, which is 1 over the square root of x plus 2 plus 1. If I try to use direct substitution now and using my limit laws, I am not going to run into a problem of having 0 in the denominator. So if I plug in -1, I'm just going to get 1/2. Now we're going to evaluate a limit in which we can show you how you can use the simplification of complex fractions to find a limit when you run into the problem of getting 0 in the denominator. So if you notice in this example, I have the problem of getting 0 in the denominator if I use direct substitution with the limit laws. So I need to use some algebra manipulation to figure out a way to determine the limit without going into direct substitution right away. So I'm going to take my expression and see if I can manipulate it a little bit to help me out. So here I have a complex fraction. I'm going to write this over 1. So this is what I call the big fraction, where I have this denominator and this numerator. And then in green I have the little denominator. That's what I like to call the little fractions. So when you have a complex fraction, what you want to do is you want to clear the fractions within the fractions. So you want to find the common denominator with all the little fractions. And the common denominator with all the little fractions is going to be 2 times 1, which is 2, times x plus 1. So I'm going to multiply the top and the bottom of this fraction times 2 and x plus 1. Okay, so I'm going to take this times this times this, and then this times this. So when I multiply by the first fraction, the x plus 1's disappear, and you multiply that by the 1 over x plus 1, so the x plus 1's disappear, and you're left with the 1 times the 2, which is 2. And then when I multiply it by the second fraction on the top, the 2's disappear, and I'm left with x plus 1. Now in the denominator, nothing disappears, and I'm left with x minus 1 times 2 times x plus 1. So now, if I clean up the numerator, I'm going to get a negative x plus 1 when I clean up the numerator. And then in the bottom, I still have 2 times x minus 1 times x plus 1. And then, if I factor out a negative 1, I get a negative, and then I have x minus 1 all over 2 times x minus 1 times x plus 1. And now I have a factor that's the same in the top and the bottom that I can get rid of. And so I'm left with a negative 1 over 2 times x plus 1 when I simplify that complex fraction. So now let's try to take the limit as x approaches 1 of our new expression. So the limit as x approaches 1 of negative 1 over 2 times x plus 1. Now I'm not going to run into any issues. So I can use direct substitution and evaluate using the limit laws. So when I do that, I get negative 1/4. And you can always verify this by graphing the function and making sure that as you approach 1 from the left and from the right, it's getting closer and closer to -4 for the value of y. Okay, so here's another example when the limit laws don't apply. So if you notice, both of the functions, if we look at these separately, this one and this one separately, both of them have an issue at x equals 0. So we're not going to be able to use the limit laws and direct substitution as of right now. But again, we can always try to use algebra to make some manipulations so that we can eventually use direct substitution and the limit laws. So in this example, since they're two separate fractions, I'm going to try to use algebra to combine the fractions and see if I can simplify anything. So I'm going to rewrite my expression by combining my fractions. So this is just another tool in our toolbox in order to manipulate expressions to use the limit laws. Now I'm showing you all the common ones, right? We talked about factoring, we talked about conjugates, we talked about simplifying complex fractions. Now we're talking about combining fractions. These are all the most common tools or the most common methods that you can use for manipulation. That doesn't mean these are the only ones, but these are the most common. Okay, so I am going to combine my fractions, but before I do so, I have to create a common denominator. So I'm going to multiply the top and the bottom of this first fraction by x minus 5, and that way I have a common denominator now. So I have 1 times x minus 5 on top for the first fraction over x times x minus 5 for the denominator plus 5 over x times x minus 5. Now I can combine, so I have x minus 5 plus 5. When I combine the tops, that gives me an x, and I have that all over x times x minus 5. Now because I have the same factor on the top and the bottom of x, I can get rid of that. And now I'm left with 1 over x minus 5. So let's try using direct substitution and limit laws now. So I'm going to try to take the limit as x goes to 0 of 1 over x minus 5. When I do that, I get negative 1/5. So you can graph this function on your graphing calculator and double check it by looking to see, as you get closer and closer to 0 on either side of 0, that you're getting closer and closer to the value of negative 1/5. So now we're going to revisit one-sided limits. And so we can use the limit laws for one-sided limit provided that the conditions hold true. So if we look at the function square root of x minus 3 for our example, we're going to evaluate the limit coming from the left and coming from the right of 3. So looking at part A first, you see that the function, the square root of x minus 3, is defined over the interval from 3 to positive infinity. Like, so to the right of 3 and up, it's all defined. But looking at the left, it is not defined if we look at the left of 3. So we can't use the limit laws to compute the limit as x approaches 3 from the left. And in fact, because the function is undefined to the left of 3, the limit as x approaches 3 from the left doesn't exist. So we're just going to put DNE here. But now if we look at it coming from the right, because the function does exist to the right of 3, coming in from the right, we can apply the limit laws. We're going to use the root law and say that the limit as x approaches 3 from the right of the square root of x minus 3 is the same as finding the limit as x approaches 3 from the right of x minus 3, and then take the square root. And when we do that, when we plug in 3, we're going to get 0, and then when we take the square root of 0, we get 0. And as you can see, as I'm coming from the right, I'm approaching the y value of 0. Now we're going to evaluate limits of a piecewise function. And we're going to look at the one-sided limits as well here. So when we're looking at one-sided limits with the piecewise function, we want to make sure that we're looking at the correct piece of the function. So if I call this piece number 1, this is the function we use for piece number 1. And if I call this piece number 2, this is the function that we use for piece number 2. Notice that I want to evaluate the limit as x approaches 2 from the left. And if we're coming from the left, we're looking at values that are smaller than 2, like 1, 1.5, 1.7, 1.9, 1.99. We're getting closer and closer to 2, but we're coming from the left-hand side, which means when we evaluate this limit, we want to look at the first piece, because this piece is defined when x is less than 2. And since we're coming from the left and we're looking at values that are less than 2, we want to use 4x minus 3 to evaluate this limit. So I'm going to replace f of x with 4x minus 3. So I'm going to take the limit as x approaches 2 from the left of 4x minus 3. Now, if I'm coming from the left, if I'm looking at this, all my values are defined heading up to that value as we get closer and closer to 2. So I can use the limit laws here, and I can just use direct substitution because I know I can rewrite this using limit laws, and that's essentially what I'm going to end up doing is substitution. So if I plug in 2, I'm going to get out 5. And as you can see, as I get closer and closer, 1, 2, 3, 4, 5. I'm getting closer and closer to the y value of 5 as I get closer and closer to 2 from the left. Now, for this one here, I want to find the limit coming from the right now. So coming from the right, my values of 2 are going to be bigger than 2. They're going to be close to 2, but they're going to be greater than 2. So we're looking at values like 2.1, 2.01, 2.001. So now we're going to be using this function here. So I'm going to plug in, for f of x, I'm going to replace it with x minus 3 squared. So I'm going to have the limit as x approaches 2 from the right of x minus 3 squared. Now, as I approach from the right, all these values are defined. So I can use the limit laws here. And I'm just going to use direct substitution because that's essentially what we're doing with the limit laws when we break it down. I'm going to plug in 2, and I'm going to get negative 1 squared, which is a positive 1. And we can verify this from the graph. As I get closer and closer to 2 from the left, I'm getting closer and closer to this value here, which is 1. Now, if I want to find the two-sided limit, as x approaches 2 from the left and from the right, because the left and the right-sided limit are not equivalent, the 1's 5 and 1's 1, this two-sided limit does not exist. So far, the techniques that we've talked about work really well with algebraic functions, but we haven't talked about evaluating limits with the basic trig functions, such as cosine or sine. And so the next theorem we're going to talk about is called the Squeeze Theorem, and sometimes you'll also hear it called the Sandwich Theorem. And this is very useful for establishing limits with the basic trig functions. Because there isn't a whole lot of algebraic manipulation that you can do with just the limit of cosine or the limit of tangent. There's not a whole lot you can do there. We have this other technique called the Squeeze Theorem. Now, that's not to say that you can't use this with algebraic functions, but it's typically used with trig functions. And so what this Squeeze Theorem says is that if you have a function that's sandwiched between two other functions, so we'll write it down like this, f of x is less than or equal to g of x, which is less than or equal to h of x. So that g of x is sandwiched between the f of x and the h of x. And if we know the limit for f of x and h of x, and they're the same, then g of x has to be the same. So if I take the limit of f of x as x approaches a, and I take the limit of g of x as x approaches a, and then I do the same thing over here, the limit as x approaches a of h of x. If I know that the limit of f of x and the limit of h of x is both the same, so if we look over here at the graph, I come across here, the point A is exactly the same. I'll call it L for limit. If these are both L, and it's sandwiched between, and g of x is sandwiched between L and L, then the limit of g of x as x approaches a has to be L. If it's greater than or equal to L and less than or equal to L, then it has to be L. That's the only option. So when something is sandwiched between two functions and we know that the limit on either end is L, then the middle limit has to be L. And that's why they call it the Squeeze Theorem, and sometimes you hear it called the Sandwich Theorem. We are going to find the limit as x approaches 0 of x times cosine of x using the Squeeze Theorem. If you look at the graph, in green, you have the absolute value of x, and in blue, you have minus the absolute value of x because it flips it as a reflection over the x-axis. And that function in between, I'll do it a different color so it's easy to see, that x cosine x is squished between those two functions. So if I set up an inequality and I say x cosine x is between the absolute value of x and negative absolute value of x, and then I take the limit of all three pieces, so I have the limit as x approaches 0 of negative absolute value of x, and then I take the limit of x cosine x as x approaches 0, and then I take the limit as x goes to 0 of absolute value of x. If I know this is 0 just by substitution and limit laws, and I know this is 0 by substitute limit laws, then I know that the limit as x approaches 0 of x cosine x has to be 0. If it's less than or equal to 0, or it's greater than or equal to 0, it's got to be 0. Now this one was fairly easy to also just use direct substitution. But there are times with trig that you can't use direct substitution, and so this is a really handy way to do this, is to squeeze it between two functions that you know it lies between, and show that if it's less than or equal to a certain value and it's greater than or equal to that same value, then the only option is it for it to be equal to that value. Okay, so here's an example of a trig limit that we can use algebra for. So when I talked about the squeeze limit being used for trig functions a lot, that doesn't necessarily mean that that's the only way you can evaluate trig functions. You can use algebra techniques on trig functions as well. So for this limit, we can use the conjugate. So I can't directly plug in 0 for theta. It's not going to work here because we're going to get 0 on the denominator. But I can use conjugates here. Conjugates work well for trig functions as well. So I'm going to rewrite the expression 1 minus cosine theta over theta by multiplying by the conjugate on the top and the bottom. So I'm going to multiply by 1 plus cosine theta on the top and the bottom. So when I distribute the numerators, so I take 1 minus cosine theta times 1 plus cosine theta. Remember, the middle terms disappear, and that's the trick to the conjugates. So I'm going to get 1 minus cosine squared theta, and that's going to be all over theta times 1 plus cosine theta. Now, if you remembered your trig identities, 1 minus cosine squared theta is equivalent to sine squared theta. If you recall, make a little note down here, because cosine squared theta plus sine squared theta is equal to 1. And so you can subtract cosine squared theta from both sides, and you get that 1 minus cosine squared theta is equal to sine squared theta. So now that's sine squared theta over theta times 1 plus cosine theta. Now I can split this up. I'm running out of room, so I'm going to finish it down here. I'm going to split this up into two functions. I'm going to split it up into sine theta over theta times sine theta over 1 plus cosine theta. And the reason I did this is because I remember from our first lesson that this limit as theta approaches 0 is equivalent to 1. This is a very famous limit. The limit, and you'll probably use it enough that you'll remember that after you start using it quite a bit. This limit is very famous. And in the first lesson, if I remember correctly, we used tables to identify that this limit was 1. So now I've got two functions here. I don't have any issues with plugging in 0 anymore, because I know that this limit exists, and I know that this limit exists, because if I plug in 0 for this limit, I know I don't have any issues of getting 0 in the denominator. So now I can use the product rule where I take the limit as theta goes to 0 of sine theta over 0 times sine theta over 1 plus cosine theta. And I can split this up into two limits. I can write this as the limit as theta goes to 0 of sine theta over theta times the limit as theta goes to 0 of sine theta over 1 plus cosine theta. I know that this limit is 1 times, and when I plug in 0 for sine over 1 plus cosine theta, I'm going to get 0. So my final limit of this up here, what we originally got that we manipulated, this limit is 0. And this is a pretty common limit too that you'll probably use over and over again. So I would make sure that you have these two limits that I just boxed in. These are common enough that you'll probably want those written down on your reference sheet. You'll use them frequently.